So let's now look at an extended example here to build an ad hoc syntax-directed translator. So to do this, we build on a bottom-up shift-reduce parser. So we assume that we can associate a snippet of code with each of the productions we have in our grammar here. At each reduction, the corresponding snippet would actually be directly executed, and we would allow arbitrary code to provide complete flexibility here. So this would include the ability to do things that, well, are usually not quite the right thing to do inside of a compiler. So similar ideas also work for top-down parsers, but since we are basing our future developments here on a Yacc-based parser, we'll take a look at how to do this with a bottom-up shift-reduce parser. So to make this work, we need names for attributes for each symbol on the left and right-hand side of an expression. Typically, we need an attribute that's passed through the parser and some additional arbitrary code, so like structures, globals, static variable information. And we've already seen that Yacc introduced these shorthands $$ for the left, and then $1, $2, and so on for the additional elements of an expression, so of a production in our grammar here, which means, well, we need an evaluation scheme, and this evaluation scheme should fit nicely into an LR1 parsing algorithm. So let's take a look at our example expression grammar. And what we want to do here with our example expression grammar is we want to introduce the cost of expressions to this grammar. So actually what we want to achieve here is not only parse an expression, but we don't want to obtain our result of our expression, but we want to obtain, for example, how long it would take to calculate the expression. So this would mean we need information about the cost for arithmetic operations, so the cost for an addition and a subtraction. And you probably know that a multiplication or division is well more complex than doing adds and subs. So essentially the cost of multiplying two values might be higher than for adding, and division might even be more costly. So what we do here is, in our expression grammar at each of these productions here, we now have this ad hoc code, which we've seen already you can use in Yacc. And in this ad hoc code, we just do a calculation and we add a value to our costs. So this is a cost function that actually returns the value for a type of operation like store, add, sub, mul, or diff. So the only thing we do here, we don't compile anything. We just use our grammar here to accumulate the costs. And finally, when we arrived at our start symbol somewhere up here, we have the accumulated cost for the whole expression here. Now, in addition to storing, in addition to adding, subtracting, multiplying, and dividing values, if we want to evaluate the real-life costs of something, we also need to have the costs of storing a value to memory. And if a value hasn't been loaded into a register so far, we also need to add the costs of loading a variable into a register from memory. So if we have a factor that evaluates to this production identifier here, what we do is we take the hash value of this identifier here, and then we check in our hash table. So this is of course a very simplified code that doesn't walk through our list assigned to the attached to our hash value here. But nevertheless, if we could find the information that in our symbol table here, the identifier behind this hash value is already loaded, well, then loaded is true, that's fine. But if it's not loaded, we need to load it into a register from memory so far. So if the indication in our symbol table says, yeah, there is some entry, but it's not loaded yet, then we need to add the cost of a load in addition to, well, adding the costs for operating on that value here. And afterwards, we set this loaded value to true. Now in this grammar on the previous slide, something was missing because we only added to this cost variable here, like that expression here, but we never initialized this. We could do this in a Yacc grammar by initializing it in main, but we could also use this neat little trick here I'm going to show you to do this right in the context of our grammar, so you don't have to have this information at some other part of your program. And you do this by just adding a new start production here. So you have a new start symbol start here, and that has one production which resolves to init and then our block we've seen before. And now this init production just resolves to an epsilon, so it doesn't consume any input token. But still, even if it doesn't consume any input token, we can attach a rule to it that just tells us what to do in this case. So in this case, it's just initializing our variable cost to 0. And since this is done before all the rest of it, well, we know our variable would be initialized. So this splitting of a production to create a reduction in the middle of such a rule here, for the sole purpose of hanging an action there, is very common. So this trick has many uses, and one of the use cases you've just seen here is just to initialize a variable to a value. So of course that was just our pseudo notation for grammar, so that wasn't yuck. So we could write a yuck grammar like this, and you see this looks very similar. We've replaced some of the symbols in our ad hoc notation here by the symbols yuck expects. So we replace this arrow here by a colon, and well, we replaced the multiplication and division signs by some ASCII characters we actually have on our keyboard here. And then on the right hand side, instead of cost, we use our dollar notation again. So whatever, if we have a expression which adds a term to another expression here, we know we have cost of a sub-expression on the right-hand side, so this term is $3 here. We have the cost of the sub-expression here on the left-hand side, $1. We add the cost of performing this addition on the two intermediate results from returned from expression and term. And finally, we assign this whole sum of our new cost here to the left-hand side. What else do we have? Well, we have this identifier again, which is again a very simplified form of it. So essentially this also now uses $, instead of cost to return information about the updated cost. So this is an excerpt. We'll put our complete YAC and LEX code for this online for you to play around with. So this cost example here might seem very arbitrary because that's not the usual, use case of a compiler, I'd say. But still, it makes much sense, especially if you consider applications like compiling code for embedded systems, because you can find very much information about what we call non-functional properties of a program. So if you could model properties, for example, for CPU instructions, like you see here, an excerpt from a datasheet of a CPU, where it shows a divide might take somewhere between 4 to 20 cycles, whereas a multiplication might take 3 cycles. Multiplication and accumulate might take 3 cycles, or in some cases 1 cycle, and so on and so forth. So if you have a processor that actually has information like this available, you could actually figure out how many processor cycles, so how much time the evaluation of a function would need. And this is very often used in much more complex, obviously, analysis than we show here, in things like worst case execution time analysis. So worst case execution time analysis means that you have a sort of a real-time system. So this real-time system, whenever an event occurs, has to react to this event in a maximum amount of time. For example, if you have your ABS, your anti-lock braking system in your car, and so you hit your brake pedal in your car, and then of course the ABS system has to react in a certain number of micro or milliseconds to produce the result of should this particular wheel brake or not, depending on some sensors it reads. And if it would take like 2 seconds instead of 20 milliseconds to do this, maybe you've already hit the tree on the road when the road was slippery or something like that. So that's not a good idea. So worst case execution time analysis would use information by the processor vendor for your specific processor, not only instruction set architecture, but for that specific implementation, like an STM32 something, to actually figure out what is the worst case, so the maximum amount of time that, for example, a certain expression or a certain function or our complete program would take to execute. And if this time we estimate it, like this is an upper bound, so the real time might be lower. If this time is actually below our critical time, then our program is safe to use in these circumstances. But you cannot only use it for timing analysis, you could also, for example, use this for energy analysis, which is obviously also important in embedded systems, especially if you're battery powered. So in IoT applications, that would be a major concern here. So what you have here on the right-hand side is an information, which tries to visualize the power consumption for one single AND instruction here on a certain processor. That's an X-Core by XMOS in Bristol, UK. And you see, on the right-hand side here, you have a scale. So the blue numbers or the blue fields indicate that there's a low power consumption, and red fields or dark red fields indicate that the power consumption is very high for the same instruction, just giving different operands here. And so these are 8-bit operands here, so going from 0 to 255. And if you combine these two operands here, then you can look up in this graph, well, is this a low energy consumption? So doing an AND of 0 and 0 has a very low energy consumption, or does this imply a very high energy consumption in our core? So if you replace this cost function, which we used for example to estimate timing, by a function returning energy consumption for, well, certain parameters here that are given, you would be able to estimate something like the energy consumption of your expression instead of just the time it takes. And then you could try to figure out, if I only have that and that much energy available, is this sufficient to still get a result before I run out of power for my program? Now, this is simplifying this analysis very much. We should have a separate course on this, on non-functional requirements, but unfortunately we don't have one so far. So all of this would be much more complex to assess for modern high-end CPUs, like whatever your ARM CPU in a modern smartphone, due to superscalarity, due to pipelines, due to caches, and so on. But this works pretty well for simple embedded cores like an AVR 8-bit core, which doesn't have any of these specific performance enhancing functionality. So in order to build something that would actually evaluate expressions, we would need to actually construct our syntax tree. So far, it was only implicit because, well, our productions here in our grammar ran down the recursion and back up again. But essentially, when we want to operate on it to generate code, we need to explicitly generate this abstract syntax tree. So what we do is we just assume that we have some functionality, a library or something to create trees. And for each of the nodes in our grammar that has a certain node type, we assume there are constructors for this type of node in our tree. And we assume that our stack holds pointers to nodes. And again, we assume a YAC-like syntax here. So what we could do here is whenever we need to add a node to our tree, like when we go down, so we have a non-terminal symbol on the left and we have one or more non-terminal symbols on the right here. And so if we have something like an expression tying two non-terminal symbols together, we would need to add another node, and to this node we attach then the left-hand side expression and the right-hand side term, and the type of the node is an addition node here because that was just an addition operation we evaluated. And we could do the same, of course, for our other arithmetic operations. So we have a subnode, a mult node, a diff node, and we could also have nodes at the leaf of our tree. So we could have a number node that has a certain token, and we could have an identifier node for this token we are currently investigating here. So actually you could go very far using such a simple approach. And here we'll show you an example to actually generate code. So yes, in this slide, we're for the first time really generating real machine code. In this case, to keep it simple, we're using ARM assembly. And early simple compilers really derived machine code directly from the abstract syntax tree. So we could do it right while we produce the abstract syntax tree by going through the recursions of our grammar here. Of course, we won't do it this way later because this really takes away a lot of optimization opportunities, but it's a nice example, at least if the CPU instructions fit this scheme. So this would work pretty well for example, not only ARM, but also RISC-V. So what we do here is whenever we actually encounter such a production here that does some sort of calculation, we actually emit an instruction to do these calculations. Some other cases here, like an expression, just resolving to a production term here, would just mean we copy a value over. So we copy the result of term over to wherever expression is. So that would be this instruction here. But whenever we need to calculate something, we need to emit such an arithmetic expression here. And to do this, we need additional registers here. So here we already modeled that values are kept in CPU registers, so we are not immediately concerned with loading stuff from memory or storing it back. That comes in a bit. So what we do here is we have for an addition $1 and $3, so expression and term, and we assume that the values of the result of evaluating this subordinate expression and term here are already contained in a register. So we need to take care of that. And so what we do is we add these two parameters together, so the expression and the term result. And now we need to store this somewhere. And to store this somewhere, we need a new register here because it's a new intermediate value, because we don't know if the value might be used later on. So what we do here, we have added a new function nxrec, which just returns the value, so the number of the next free register here. So whenever we have such an arithmetic expression here, we call nxrec to get a free register. This is essentially then $, and we add, putting the result of the addition into $, the parameters $1 and $3 here. So we omit the symbol table handling here, obviously, because that wouldn't fit on the slide. So we do the same for all of our arithmetic operations. Now, if we encounter a number, well, this number is somewhere directly in our code, so we could actually emit this number. So to emit that we want to reference a number, we need to load the number into a machine register here. So this is done using a load immediate instruction for a move. We'll see this on the next slide here. And of course, this also needs a register, so we need to fetch this register here. And if we have an identifier, we need to load the value of that identifier from its memory location. So we need something like an emit load for a load register command. So if you're not accustomed to ARM assembly, this is a very simple assembly language, and we'll discuss the details on the follow-up slide here. So first let's look at the helper functions we've used but not yet defined here. So first it's nxrec. So nxrec should return the next free unused register number, and we do it in a very simple way. So what we do here is we have a static int variable here, rec, for the number of the register here. And because it's a static int, it means the scope is only inside of our nxrec functions, so no other function can manipulate it. But since it's static int, it's treated like a global variable. So the first time we enter nxrec, it's initialized to 0, and then it retains its value in following calls to nxrec. So when we do a return rec ++ here, essentially, well, it keeps this value. So when we enter nxrec for the next time, we have the old value of rec ++ again. So, well, if we had an unlimited number of registers, we just would use the static int rec equals to 0 and return rec ++, and it would just return increasing numbers. Now, unfortunately, on all processors, the number of real-world registers is limited. So a typical ARM processor has 16 registers, but some of these registers are used for special functions, like a register 13 is a stack pointer, register 15 is a program counter, and so on. So let's just say we have 12 registers available. So we add an additional line of code here that checks if our number of registers is larger than 11. Then we just set our value of register to 0 again and return this one here. So we do some sort of a wraparound if more than 12 registers are used. Of course, that's not what we should do. So register allocation in a real-world compiler is much more complex than this, and it's actually one of the really complex problems where people did lots of research about how to do efficient register allocation. So in this case, it's very simplistic. So this means if we have very complex expressions, we'll actually run out of free registers. And since we wrap around here instead of giving an error message, that would be the appropriate thing to do, obviously. Then we just override existing values. So the other the other functions we've used are these emit functions to emit a certain command. So we have an emit function to emit a memory load from an address here. And you see this is a very convoluted syntax in printf. That would actually be the syntax that an assembler for ARM would actually try to use. So every instruction that's not a label in assembler must be prepended by some sort of white space. In this case, we use \t to add a tab character in front of it. And then we use this %d for register and %s for the address to actually load something to a register. So first we load the address of a variable here, and then using this second instruction, which we actually pass here, we do something with it. For example, we load the contents from that memory location, because we only loaded the address here in this register, to our register, so we can operate on that. And we can do a similar thing to li. So in li we have immediately passed the value here, which is just returned from our scanner as the YYLVAL information here. So we could emit a load immediate instruction here that loads an immediate value to one of the CPU registers. And finally, the emit function here just emits the instruction giving the two operands, the destination register and the operation like add or sub, which we want to pass. So this is pretty ugly code. What you should probably do here. So you see things like this in very early compilers. If you look at Wirt's compiler book, they actually do things like these. They even emit the binary instructions directly by putting binary constants together. This is pretty ugly and makes your compiler hard to read. So maybe you should write more elegant functions to do this. And we'll see, of course, how to do this, how to split this stage from going to the parser to emitting assembly later, because we want to use an intermediate language to do this, obviously. So let's take a look at an ARM instruction overview again of the instruction we've used. And these were the instructions we actually output using printf. So we have an instruction LDR for load register. Load register loads into a register RD the value of an address Z. And this value of an address is indicated by this equals sign here. This is pretty uncommon here, so most assemblers would use different syntax. ARM was a bit special here. So if we have loaded the address of a variable into a register, it's just a pointer to this variable in C-speak. So what we would need to do is to dereference that pointer. So if we have the address of a variable in some CPU register RS, then we could use these square brackets here to dereference it, so to load a value from this address in memory into this register here on the left hand side. And the other instructions we use is to load an immediate value, so that would be a number here like 42, and this uses the hash character here in front of this value to indicate it's an immediate value. So using this move instruction, we could directly load a register with an immediate value, and this immediate value is actually part of your instruction encoding, so you don't have to do an additional memory access. And finally, you have your pretty standard arithmetic operations, so add, sub, mul, and diff, which just takes two operands here, does the respective calculation on these two operands, and stores its result to our destination register. So let's take a look at what our compiler outputs. Yes, it really outputs valid assembler code. So the first is a valid expression here, bracket z minus 3, closing bracket, times x plus 5. And what it can do here is you see that YAC compiler by standard takes its input from the standard input, so from the keyboard. And in Unix you can do it, well, you could just type whatever. If your compiler is compiled, you could just /compile, call your compiler and type this on the keyboard. But you could also just use the pipe operator here to copy whatever comes from the previous command, so just an echo that prints these characters inside of the double quote, and these are then passed as the standard input to our compiler. And our compiler would output something like this, like, well, it would start here on the left-hand side, so it sees, oh yeah, it needs something like that. So it first needs to load the address of that into a register R0, and then it would actually need to dereference that memory here at address R0, and we load it again into R0. So we save one register here because we don't need the address of Z after that, so we can throw it away. And we do this by overwriting R0, well, by the contents of the memory address pointed by it. So these first two instructions load the value of Z into register R0. Then, well, the next thing that's encountered in this expression here is a 3. So this is an integer constant, so we emit code to load the constant 3 into our next free register, R1. Then we climb up our syntax tree, so we encounter the minus operator here, and so we need to implement the minus operator, and we know that the operands of our minus operator are stored on the left and right hand side. So the left hand side was z, so it's in R0. The right hand side is a 3, which is stored in R1. So we emit this instruction subtract from R0 the value that's in R1 and store it again in a new register here, R2. All right, so now we climb up our abstract syntax tree again. So the next symbol we encounter is x. So we do the same thing as for z before. So we load the address of x into a register and then dereference this pointer here to x to load the value into R3. Then we can climb up one level again. So we encounter our multiplication symbol here. So we need to multiply the two operands. And here we see that our syntax, by doing this recursion, our parser really remembers that the result of calculating z minus 3 is in register R2. So that's the left hand side here. And the value of x we just loaded is in R3. So we multiply our intermediate result R2 by whatever we just loaded into R3. And we need additional register to store this information in. So we store this in R4. And finally, we add our constant 5 here, like our addition before. So again, we have the intermediate value on the left-hand side, which is this part of the expression here before the plus sign, which was in R4 because we stored the result of our multiplication there. And our new constant 5 was just loaded into R5. So we have our result in register R6. Okay, hooray. And if we assembled this and added a bit of syntactic sugar, so our assembler would actually be able to eat this whole input here, then we would actually have the result of calculating this expression here, well, in register R6 later on. So we compiled a simple expression so we could build something like a pocket calculator. Now what happens if you have input like this here? So z minus 3 in brackets times x closing bracket plus 5. Now this is a syntax error, obviously. So what happens here is that this syntax error is only encountered after your compiler actually started to emit some assembler code. So, well, that's a valid expression. Z minus 3 in brackets times x is also valid. And only after it emitted all the code up to our multiplication here, it figures out something's wrong here, and it prints like syntax error. There's a closing bracket which should be there. So this would output partial assembler code while this program is scanned and parsed. So that's probably not a good idea. Well, a real-world compiler could, of course, throw away this partial assembler code, but this here is just printed out on your screen. So that would confuse the user quite a bit, I suppose. So the other problem with using our very simplistic approach is that we would really run out of registers because we only have 12 registers. And if these all continue to be used in very complex expressions, we would just run the risk of overwriting some values here. So here in our example, we have reduced the number of available registers in the nxreg function to 5 to make this example a bit shorter. And if we have an input like this, so a plus, bracket b plus, bracket c plus, bracket d plus e, for closing brackets times x, we would need, well, R0 to store the value of a, R1 to store the value of b, R2 to store the value of c. Then we need R3 to store the value of d, R4 to store the value of e. Then we need, we can start evaluating d plus e finally. So we need R5 to store the contents of d plus e. And then, well, unfortunately, well, our next addition here for C plus D plus E would then wrap around and try to store the result in R0. But this R0 still has the value of A, so we would overwrite the value of A here, which is not a good idea. So register allocation is much more complex in the real world than we've seen before. But some approach like having infinite numbers of registers can be used if you don't directly generate assembler code, but something we call this intermediate representation, which we've seen in the beginning. So you can have intermediate representations that just assume you have an infinite number of registers, and then you can defer the complex task of actually assigning physical CPU registers to intermediate representation virtual infinite register numbers to a later stage in your compiler. So a real compiler needs a method for register allocation, and this register allocation later on has to assign values to obviously free registers, so it needs to keep track of which registers are still used, which are free. And of course you can have situations when you run out of registers. This was especially common on early processors where you only had a very limited number of general purpose registers, like 4 general purpose registers on x86 CPUs. And when you run out of registers, before you would override one, you would have to spill the value of that register. Spill means you save the contents of that register to memory, so to the variable which holds the value, and then restore the value later when needed. So you need to keep track of this. As I said, efficient register allocation is quite complex, and we'll see this later in this course. But still, what we have achieved today is we have managed to generate our first, primitive assembler code for relatively simple inputs, but still these inputs can have structure, so they can be parsed. So it's a real sort of very simple compiler, which actually does something almost useful. So what's next here? So the next thing is we'll take a quick look at attribute grammars, so how to do a formal approach to try to handle type information and so on. And we'll give you some insight into type systems and type analysis, which go a bit deeper than the approaches with just a simple symbol table handling we've seen here. So that's all for today. Here's just some references which are more about all the non-functional properties, like you have software optimization guides, for example, from ARM that give you information about the number of cycles for a certain CPU core. You have this paper here by colleague Kerstin Eder and her PhD students in Bristol in the UK. So she worked quite a bit on energy-aware software engineering. If you want to have a good overview, there's a slide set by my former boss Peter Marwedel on embedded system evaluation and validation, so especially the worst case execution time analysis, and the related textbook for embedded systems has also just been published as an open access publication by Springer. So if you search for Peter Marwedel's name, you will also find a link to his textbook, which I can recommend if you're interested in embedded systems. As I said, it's now freely accessible from the Springer website as a PDF. And if you want to dig deeper, of course, to generate real machine code, you of course need to know the machine instructions your CPU accepts. So there's usually an instruction set reference guide for each CPU, like the one from ARM we've linked here. So that's all for today. Thanks for listening, and until next time.